Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss periodic functions and Fourier series, specifically complex exponential Fourier series. So in this topic, we will describe an inner product between two functions. We will define orthogonality of functions, when two functions are at right angles relative to this inner product. We will show that we can project one function onto another. We'll discuss projections onto a set of mutually orthogonal functions to get a best approximation. We will introduce the complex exponential functions. We will show that these functions are all mutually orthogonal to each other. Finally, we will approximate periodic functions with these complex exponential functions, looking at a number of examples. Suppose we have an interval from negative t over 2 to t over 2. And on this interval, suppose we have two piecewise continuous periodic functions f and g with period t. In this case, we may define the following inner product on these two functions, where we integrate the conjugate of the value of the first function times the value of the second function, integrated from t going from negative t over 2 to t over 2. That is, we're integrating over one period. Let's contrast that with the inner product of two finite dimensional vectors. Well, now instead of taking the kth entry of each of the vectors and multiplying them, we're evaluating the functions at the various values of t. Also, you will notice that the first one is conjugated, and whereas the second uses a sum, you'll recall from your first year calculus course that essentially the integral is an infinite sum. Now, this inner product has all the properties of the inner product of finite dimensional vectors. For example, the inner product of a function and itself is simply the integral of the absolute value of the function squared integrated over the interval. And because it's the absolute value squared, this must be a value greater than or equal to 0. And the only piecewise continuous function on the interval from negative t over 2 to t over 2 that has integral 0 is the 0 function. For any other function, the inner product of f and itself is going to be equal to a value greater than 0. Also, if you go back to the properties of the complex conjugate and the properties of the integral, you will find that the inner product of f and g is equal to the conjugate of the inner product of g and f. Of course, if f and g are both real valued functions, then the inner product is symmetric. The inner product of f and g is equal to the inner product of g and f. Also, the inner product of f and a scalar multiple times the function g is simply equal to that scalar multiple times the inner product of f and g. Similarly, once again, based on the properties of the integral, the inner product of f and the sum of the functions g plus h is equal to the inner product of f and g plus the inner product of f and h. These, as you may recall, were the critical properties of the inner product from which everything else we discussed can be derived. Now we can say that two periodic functions with period t, possibly including the constant functions, are orthogonal if this inner product is equal to 0. Also, we can define the 2 norm of a function, which is simply the square root of the integral of the function squared integrated from negative t over 2 to t over 2. Finally, we can also define the projection of one function onto another. That is, what scalar multiple of one function is the best approximation of another function. Now, for example, if we have the constant function f0 together with a sawtooth function f1, which is just defined as the function t on the interval from -1 to 1, we consequently have two periodic functions with period 2. And you'll notice that these two functions are orthogonal to each other, because if you were to calculate the integral of the product of these two functions from -1 to 1, you get 0. Here's another periodic function. If we define the periodic function that between -1 and 1 is equal to e to the t, and repeat this periodically forever, this also defines a periodic function with period 2. So let's find the best approximation of the function e to the t periodically extended as a linear combination of the constant function and the sawtooth function. So, doing the calculations, the projection of the periodic extension of e to the t onto the constant function is simply calculated as this ratio of integrals, and doing the math, we see that the coefficient a0 is just e minus the reciprocal of e all over 2. Similarly, the projection of the periodic extension of the exponential function onto the periodic extension of the function t on the interval -1 to 1, which is the sawtooth function, well, once again, we can do this same calculation, and this gives us that the coefficient a1 is just 3 times the reciprocal of e. Consequently, the best approximation of the periodically extended function of e to the t as a linear combination of these two periodic functions is simply the coefficient a0 times the function 1 plus the coefficient a1 times the function t. We can plot this, and we can see that, yes, indeed, this does seem to be probably as good an approximation of the exponential function periodically extended by a straight line. Next, I'd like you to consider the following collection of complex valued functions. U sub n of t is defined as e to the jn of 2 pi over t, capital T being the period, times the variable t, where n can be any integer, positive or negative. Let's calculate the integral of u sub m times u sub n. So in this case, we are taking the conjugate of the function u sub m times u sub n. Now, the function e to the jm 2 pi over capital T times t, well, that's just j times a real value. So the conjugate of that first function is simply the e to the negative jm 2 pi over capital T times t. Now we have a product of two exponentials. However, the product of two exponentials is simply the exponential of the sum of the exponents. So if we sum the two exponents and factor out that which is common, we get that this inner product is just the integral from negative t over 2 to t over 2 of e to the j times the difference of n minus m times 2 pi over capital T all times t. Again, t running from negative t over 2 to t over 2. So what is the value of this integral? Now, if m equals n, then the inner product of one of these functions with itself is simply the integral of e to the j times m minus m times 2 pi over capital T times t, but m minus m is equal to 0. J times 0 times 2 pi over capital T times t is just 0, and e to the 0 is equal to 1. So we're just calculating 1 integrated from negative t over 2 to t over 2, and you know from your calculus course that that is equal to t. Otherwise, if m is not equal to n, we are then calculating the inner product of u sub m and u sub n. And that is just that integral we see here. Now, from your calculus course, you know that the antiderivative of e to the st is just 1 over s, e to the st. Here, s is just a more complex expression, j times n minus m times 2 pi over capital T. But it's essentially the same. So now we have this antiderivative, and we just evaluate this antiderivative at t over 2 and subtract from that the antiderivative evaluated at negative t over 2. This gives us the following expression. Now, so we have that negative t over 2 in the second exponent. Well, we can bring that out. But wait a second. Once we cancel everything else out, notice that the second expression is nothing more than the conjugate of the first expression. So now we have a constant times a function minus the conjugate of that function. Now, you may recall that for a complex number z, z minus its conjugate is just twice j times the imaginary component of z. All right, so now we have e to the j times something. Well, you may recall that e to the js is just cosine of s plus j times sine of s, where s is real. So therefore, the imaginary component of e to the js is just sine of s. If we multiply that by 2j, we get, in this case, the reciprocal of what we see there on the right, the coefficient, times 2 times j times sine of n minus m times pi. All right, easy enough. We can simplify that out. But in all reality, that's just sine of an integer times pi. Well, sine of 3 times pi or sine of 8 times pi is always equal to 0. So regardless, and remember that m is not equal to n, so the denominator is not 0, and the rest is quite trivial. This is always equal to 0. What does that say? That says that if m is not equal to n, then the two functions are orthogonal. All right, so if u sub n of t is the function defined as e to the jn 2 pi over capital T times t, we have that the inner product between u sub n and u sub m as being t if m is equal to n and 0 otherwise. We can also write this as t times the cardinal sign of m minus n, where in digital signal processing, the sinc function is defined as the sinc of x is equal to sine of pi times x over pi times x, where when x is equal to 0, we just take the limit, and the limit is that sinc of 0 is equal to 1. All right, so now we have these infinitely many functions where you have one function defined for each integer, positive or negative, or use 0. What is the span of all of these functions? Well, at the very least, the span does contain all periodic functions with period t, and that includes constant functions, with a finite number of discontinuities on any one period. That's generally more than sufficient for what engineers require. Now, what do these functions look like, and why are they so useful for periodic functions? Well, u0 is just the constant function 1. U plus or minus 1 are spirals that make exactly one oscillation in the complex plane along the unit circle from negative t over 2 to positive t over 2. U plus or minus 2 makes 2 rotations within any one period. You'll notice that U sub 2 above has a spiral that is counterclockwise, whereas U negative 2 has a spiral that is clockwise, or in the opposite direction. As one more example, U plus or minus 5 are shown here. So as you can see, we simply get more and more spirals. Each of these, we are looking at how much each period contributes to the function in question. All right, so now we have to find these coefficients. These are actually called the Fourier coefficients. Specifically, they're for the complex or exponential Fourier series. Well, in this case, again, all we have to do is calculate the integrals. So a sub k is the inner product of u sub k and f over the inner product of u sub k with itself. We've seen previously that the denominator is just t for all k. The numerator is the conjugate of u sub k times f, and e to the j times an expression that is real conjugated is just e to the negative j times that expression. So this simplifies to this calculation here. Now, it still doesn't look nice, but it is an exponential times a function, and in many cases you can apply integration by parts to get a simpler solution. For example, if we're dealing with polynomials, integration by parts can be used to reduce the power or the degree of the polynomial. And for small polynomials, this can be calculated quite quickly. Also, if f of t is a real periodic function with period t, then it happens that a sub negative k is equal to the conjugate of a sub k. What that means is we only actually have to calculate a sub k for k going from 0 to however large we wish. Also, because of that, we can calculate this sum. But there's actually a little bit of simplification that goes on here, which makes life really easy, because we're essentially adding an expression plus its complex conjugate. Consequently, without going through the math, once we have found a sub k, then we get that this is actually equal to twice the absolute value of a sub k times cosine of k 2 pi over the period times t plus a phase shift. And the phase shift is the argument or the angle of the calculated coefficient a sub k. So immediately from the coefficients a sub k, we can calculate the amplitude and the phase shift. That's actually very convenient because now you actually understand how much this cosine is shifted on away from a pure cosine. Now, so consider the periodic extension of the polynomial t on the interval from -1 to 1. So the period is equal to 2, and the function on that interval is simply repeated over and over again on subsequent intervals. This is the sawtooth function, or a sawtooth function. We can calculate the coefficients. So we can calculate the coefficients a0 through a5, and notice that they are all j times a scalar, plus or minus. Okay, that makes life a little bit easier because now we can see that our approximation is, well, in the first case, the absolute value of negative j over pi is just 1 over pi times 2, so the coefficient is 2 over pi. That's for a1. The phase, or the angle, of negative j over pi is negative pi over 2, or negative 90 degrees. So the first term is just 2 over pi cosine of pi times t minus 90 degrees, and so on and so forth for the subsequent terms. a0 is, of course, 0, so there is no constant term. We can plot this approximation, and we can see it's not amazing, but it's actually not bad. It's about as close as we can get with these 5 cosine functions. As another example, consider the periodic extension of the function 1 minus the absolute value of t, again on the interval from -1 to 1. This creates a periodic tent function. Once again, we can calculate the coefficients, and then from those coefficients we may deduce that the approximation of this periodic tent function is given by this cosine. Notice that all of the coefficients are real, therefore the argument of each of them is equal to 0, so there is no phase shift. And if we plot this approximation, we can see that the approximation is pretty good, specifically because this is a continuous function as opposed to the previous function where the sawtooth function was discontinuous at the endpoints of the interval -1 to 1. All right, now let's consider the periodic extension of the polynomial that has roots at 1, -1, and 1/2. If we periodically extend this from the interval -1 to 1, this creates a non-symmetric wave. So we can still calculate the exponential coefficients, but we now note that they are complex, being neither entirely real or imaginary, except of course for the constant, or the dc term. We can then calculate the absolute value of each of these coefficients, multiply by 2, and calculate the argument. And therefore we can see that we can approximate this non-symmetric wave reasonably closely using 5 terms. In fact, if you take a look, the terms quickly do get quite small, and so even if we were to use only the first 4 terms instead of all 6, we'd still get a reasonable approximation of the periodic function. The point here is, what this says is that as an engineer, you can approximate a continuous periodic signal with a reasonably small number of oscillators, each generating a signal at a different frequency and adding the results appropriately. All right, here's the Maple code if you want to try this. First, restart to reset the system. We're going to define the period. So t is assigned the value 2. In Maple, := is the assignment operator, while a single equals is a check for equality. We're now going to define the function p, which we will periodically extend from the interval -t/2 to t/2. So in this case, it is the polynomial that has roots at -1, 1, and 1/2. Next, we're going to calculate 6, or coefficients, from a sub -5 to a sub 5. Being engineers, we want to use j as the square root of -1, so we will set the interface imaginary unit to use j. All right, so now we can have a for loop. So k will take on the values from -n to n. In this case, n is assigned 5, so -5 to 5. And we will calculate a sub k for each of those values of k. So that's the integral of the conjugate of the function, so negating the exponent, times the polynomial integrated on the interval from -t/2 to t/2, all divided by t. We can now plot both the function on the interval from -t/2 to t/2, and then we will plot the approximation a little bit further out, so you can see that it is indeed a periodic extension of the polynomial p of t. Finally, we will write down the sum as a sum of, or the DC term a0 plus the cosine functions with the appropriate phase shift. There are, of course, other orthogonal functions that are periodic. For example, the most common, and which you'll probably see in your calculus courses, are the constant function and then cosines and sines with progressively higher integer frequencies. Now, because these are sines and cosines, it may be easier to visualize. However, it's going to be more frustrating to calculate because now you have twice as many integrals, and those integrals are not involving exponential functions, but rather they're involving trigonometric functions. So that may actually be more frustrating than you'd prefer. Also, a phase-shifted cosine is easier to understand than the sum of two trigonometric functions. So, for example, on the left-hand side, we immediately see the amplitude is 1.97, and the phase shift is 40 degrees. On the right-hand side, it's not really clear, even though the right-hand side equals the left-hand side. It's not really clear that what the amplitude is, nor can you easily deduce what the shape is going to be. You don't have the phase shift. So the complex exponential Fourier series is actually ultimately much easier to calculate and to use the results therefrom. The only issue is you have to use complex numbers. So, following this topic, you now understand the concept of an inner product between two functions. Again, it's an integral where the integrand has the first function conjugated multiplied by the second function and integrated over the interval. You know now that two functions can be orthogonal or at right angles with respect to this new inner product. You know how to project one function onto another, and you're aware that the sum of projections onto orthogonal functions gives the best approximation of the given function in terms of a linear combination of these orthogonal functions. You know specifically about the complex exponential functions u sub n of t defined as e to the jn 2 pi over the period capital T times t. You know that these are orthogonal and they form a basis for functions of period t, specifically as long as they are piecewise continuous with a finite number of discontinuities on any one period. We've also seen examples of how we can approximate periodic functions with a finite number of these complex exponential functions. If you wanted a better approximation, you would increase the number of terms, but if you can deal with a poorer approximation, you do not need all of the terms in question. What this says also is that you can approximate any periodic signal you want to generate by simply combining the signals of oscillators, each producing signals at different frequencies. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!